Hello there, and welcome to Sleepy Science Vault. There is a moment, far beyond anything we can properly imagine, when the last light will fade, not with an explosion, not with fire, but with silence. For most of human history, when people imagine the end of everything, they pictured destruction. A great collapse. A final blaze. But the scientific picture of the universe's true ending looks nothing like that. It is slower, quieter, almost gentle in its own vast and patient way. Scientists call it heat death. And despite the name, it has nothing to do with heat at all, not really. It is, in truth, the opposite. Many researchers prefer another name for it entirely, the Big Freeze, because what actually awaits the universe is not a burning finale, but an extreme, endless cold. A stillness so complete that nothing more can ever happen again. Let that sit with you for a moment. Not an ending of fire, but an ending of cold. It's a strange thing to consider, how the universe began in overwhelming heat, in the blinding brightness of its first moments, and yet its distant future points toward the opposite extreme. Where the beginning was almost unbearably hot and dense, the far future stretches out into deep, dark, and unimaginably cold quiet. This is why the phrase Big Freeze fits so naturally. It captures the true character of what physicists believe is coming, not a catastrophe, but a fading. A universe that doesn't end in a moment, but dissolves, gradually, over spans of time so enormous that comparing them to the age of the universe so far would be like comparing a single breath to the entire span of human history. Slowly, the universe grows colder and darker. Not all at once, but continuously, endlessly, star by star, galaxy by galaxy, era by era. To understand how something so gradual could be called an ending at all, it helps to think of the universe's future not as a single event, but as a long procession of eras. Right now, we exist within what's sometimes called the stellar era, a period defined by starlight. Stars forming, burning, living out their long fiery lives, and eventually dying. This era, as impossibly long as it already seems from our human perspective, is really just an early chapter. Beyond it lie later eras, ages where matter itself becomes less and less active. Where the raw material that once built stars and planets slowly stops behaving the way it does now. Fusion fades. New star formation becomes rarer, and then rarer still. And eventually, the very things that create light and warmth and structure begin their long transition toward stillness. It is a bit like watching a great fire. Long after the last log has been added, the flames don't vanish immediately. They flicker. They shrink. They give off less and less light, until finally, all that remains is the faintest ember, and then, nothing visible at all. Just warmth radiating outward into a dark and silent room. That, in many ways, is the shape of cosmic time. What makes heat death particularly fascinating, and admittedly, difficult for the human mind to fully grasp, is that it isn't envisioned as some violent breaking point. There is no moment where the universe suddenly shatters or collapses inward. Instead, most descriptions frame it as a state of near-perfect equilibrium. Uniform, balanced, smooth in every direction, with nothing standing out, Nothing concentrated, nothing distinct. Imagine a cup of hot tea left on a table. At first, the heat is concentrated in the liquid, warmer than the air around it. But slowly, imperceptibly, the warmth spreads outward until the tea in the room reach the same gentle, unremarkable temperature. No more flow of heat happens after that, because there's no more difference left to drive it. Now imagine that same principle, playing out not in a teacup, but across every star, every galaxy, every particle in the observable universe. That is heat death, in its simplest form. Not cold in the way we experience cold now, on Earth, in winter, but an ultimate, total evenness. A universe where every pocket of energy has spread itself out entirely into the vast openness of space, where nothing is warmer or cooler than anything else, where all the distinctions that make change, motion, and life possible have quietly disappeared. Some scientists describe this more directly, calling it a cold death outcome, emphasizing that whatever word we use, heat death, big freeze, cold death, they're all pointing toward the same eventual truth. Not fire. Not collapse. Just cold. Endless, gentle, total cold. And perhaps the most poetic way to understand why this happens comes from a deceptively simple phrase, used by some to describe the process. The universe, they say, is running out of difference. Not running out of heat, exactly. Not running out of matter, or energy, or stars. Running out of contrast. Running out of the gaps, the imbalances, the differences between one place and another that make anything happen at all. Think about what difference really means in this context. A waterfall only flows because there's a difference in height. A breeze only blows because there's a difference in air pressure. Heat only moves because there's a difference in temperature. Every process we recognize as motion, or energy, or life, or light, all of it depends on some kind of imbalance somewhere. Some difference waiting to even itself out. The universe, across its long future, slowly erases these differences. Bit by bit. Star by star. Galaxy by galaxy. Until eventually, there's nothing left to even out, because everything already is even. So why would something like this happen at all? Why would the universe move, so persistently, toward this quiet, uniform stillness? The answer lies in one of the most fundamental principles in all of physics, the second law of thermodynamics. It's a beautifully simple idea, even if its implications are almost unimaginably vast. The second law states that in any closed system, entropy, a measure of disorder, or perhaps more helpfully, a measure of how spread out and mixed energy has become, tends to increase over time. Not decrease. Not stay the same. Increase. This is why ice melts in a warm room, but a puddle of water never spontaneously freezes into a perfect ice cube on its own. Why a drop of ink spreads through water, but never gathers itself back into a single drop again. Nature has a direction, a preference. And that preference is toward greater disorder, greater mixing, greater evenness. Apply that principle not just to a cup of water, or a room, but to the entire universe, and you begin to see where all of this is heading. Physicists describe this trajectory as movement toward a state of maximum entropy. a point where energy is spread out as completely as it possibly can, where there is no further mixing left to do, no more disorder left to increase, because everything that could become disordered already has. At that point, something remarkable and strange happens. Even though energy still technically exists throughout the universe, it becomes impossible to use it for anything. Not because it disappears, but because using energy always requires some kind of difference to draw from. A hot region next to a cold one. A high point next to a low one. Without contrast, without imbalance, there is nothing left to power a process, a movement, a spark, a flame, a heartbeat, a thought. Energy, spread perfectly and evenly across all of existence, becomes unusable. Present, but inert. There, but silent. No more starlight forming. No more motion driven by temperature or pressure. No new structures, no new stories, no new events unfolding anywhere in the vast, dark and expansive space. Just balance. Just stillness. Just an infinite, quiet, cold equilibrium stretching outward, forever. It's worth pausing here, letting that thought settle gently in the mind, because it is genuinely one of the strangest ideas in all of cosmology. Not an explosion. Not a collapse. Not a war between forces tearing the universe apart. Just a slow, patient drift toward complete and total balance. A universe so evenly spread that nothing more can ever happen within it again. And somehow, there's something deeply peaceful in that image. Not frightening, not violent. Just quiet. Just still. The final, gentle exhale, at the very end of time itself. Somewhere in the long unfolding of cosmic time, there comes a point where the universe begins to run out of things left to do. Not suddenly. Not dramatically. But gradually, the way a river slows as it widens, the way a fire dims as it consumes the last of its fuel. As entropy continues its patient climb, fewer and fewer physical processes remain possible. Fewer stars ignite. Fewer chemical reactions occur. Fewer places exist where energy can still move from one state to another. The universe doesn't stop all at once, it simply has less and less left to spend. This is the heart of what physicists mean when they describe the universe approaching thermodynamic equilibrium on a cosmic scale. It's a strange phrase to sit with, at first. Equilibrium sounds peaceful, almost pleasant, like balance, like harmony. And in a way, it is exactly that. But it also means something quietly final. It means that every difference, every gradient, every imbalance that once allowed things to happen has smoothed itself away. Once equilibrium is truly reached, one of the most important features of the universe simply vanishes. Temperature differences disappear entirely. Every corner of space, every remaining particle, exists at exactly the same temperature as everything else around it. No warmer regions. No cooler regions. No pockets of contrast anywhere, in any direction, for any distance you could travel. It's worth remembering just how much of what we consider activity in the universe depends on exactly these kinds of differences. Heat moving from a warmer object to a cooler one. pressure pushing from a denser region to a thinner one. Energy flowing, always, from where there is more of it to where there is less. Without temperature or energy gradients left anywhere, none of that can continue. Stars can no longer shine, because starlight depends on constant differences in temperature and pressure deep within their cores. Engines, of any kind, anywhere, can no longer run, because every engine, whether built by nature or by hands, depends on some difference to convert into motion. Even chemical systems, the quiet reactions that build and break molecules, slow and then stop, because they too rely on some imbalance to drive them forward. There is no more useful work left to extract from a universe like this. Not because the energy has vanished, it hasn't. It's still there, still real, still present in every remaining corner of space. But it has nowhere left to flow. Nothing left to power. Nothing left to change. Some descriptions of this final state try to capture it in the simplest possible terms. Every single point in space, they say, eventually reaches the exact same temperature. Not almost the same. Not nearly identical. The same. A universe so perfectly balanced that if you could stand anywhere within it, in any galaxy, in any long-abandoned corner of space, the reading on a thermometer would never change. It's a strange kind of stillness to imagine. Not silence in the way we experience it here on Earth, where sound waves stop moving through air, but a deeper, more absolute quiet. A stillness where the very possibility of difference has been erased. This is why some scientists describe heat death using two measurements at once. Minimum temperature, they say, paired with maximum entropy. As strange as it sounds, these two ideas are really describing the same ending, seen from two different angles. Maximum entropy means the greatest possible spreading out of energy, the greatest possible mixing, the point where no further disorder can be added because none is left to add. Minimum temperature reflects what that spreading actually feels like, physically, everywhere at once. An almost imperceptibly faint warmth, spread so thin across the vastness of space, that it settles into something close to absolute cold. Two ways of describing one truth. A universe that has used up all of its differences, and in doing so, has used up all of its possibilities for change. But here's where the story becomes even more interesting, because heat death isn't simply something that happens automatically, no matter what. It depends entirely on one particular condition holding true, across the entire future of the cosmos. For heat death to actually occur, the universe has to keep expanding. Forever. It cannot pause. It cannot reverse. And most importantly, it cannot ever recollapse back in on itself. This might sound like a small detail, but it's actually one of the most important branching points in cosmology. If the universe were to someday stop expanding and instead begin contracting, pulled back together by its own gravity, the story would be completely different. Instead of a slow fade into cold stillness, the far future might involve galaxies rushing back toward one another, temperatures rising instead of falling, density increasing instead of thinning out. Some have imagined that scenario ending in a kind of mirror opposite of the Big Bang, a big crunch, rather than a big freeze. But that isn't the picture supported by what we currently observe. Instead, the expansion of space appears to continue, not just onward, but outward, indefinitely. Galaxies drifting farther and farther from one another. Distances growing, not shrinking. Space itself stretching continuously across unimaginable stretches of time. And there's something even more remarkable happening within that expansion. It isn't just continuing. It's accelerating. This detail, more than almost any other, is why heat death remains one of the leading pictures scientists hold for how the universe's story eventually unfolds. Observations of distant galaxies show them moving away from us not at a constant pace, but at an ever-increasing one. Something is pushing space outward, faster and faster, rather than allowing gravity to slow that expansion down over time. The implications of this are almost dizzying to consider. If expansion is accelerating, then not only will the universe never collapse, but distant galaxies, distant clusters, distant regions of space that we can currently observe, will eventually move away from us faster than light itself can cross the growing gap between us. When that happens, those regions don't just become far away. They become permanently unreachable. Not because of any physical barrier, but because the space between here and there is expanding faster than anything, even light, could ever cross it. Picture that for a moment. Somewhere out there, right now, exists a galaxy whose light still reaches us tonight, faint and ancient, crossing unimaginable distances to arrive here, in this moment, in your sky. But someday, that same galaxy will slip beyond an invisible horizon. Its light will still be traveling toward us, technically, but the space between us will be growing so quickly that light will never actually complete the journey. One by one, silently, without any dramatic event marking the moment, distant galaxies will fade beyond reach. Not destroyed. Not extinguished. Simply, gone from our view, forever, swallowed not by darkness, but by distance itself. This is the quiet, expanding stage upon which heat death slowly unfolds. Not a universe crushing back down into a single point, but one continuously loosening, spreading, thinning, every galaxy drifting farther from every other galaxy, every connection slowly stretching until it can no longer hold. And within that vast, ever-widening emptiness, the long transformation continues. Matter cooling. Energy spreading. Differences fading. Moving, gently and irreversibly, toward that final, perfectly balanced stillness, where nothing more is left to happen, anywhere, ever again. There is something quietly strange about the way isolation happens in the universe. It doesn't arrive suddenly, the way isolation often does in human experience. No single moment marks its beginning. Instead, it builds slowly, region by region, gap by gap, until eventually, isolation simply becomes the nature of things. Because expansion continues to accelerate, the observable universe, the portion of space we can actually see and measure and study, becomes increasingly cut off from everything beyond it. Not because anything is destroyed. Not because anything vanishes. Simply because the space between here and everywhere else keeps growing, faster than anything could ever cross it. Scientists describe this using the idea of a cosmological horizon. Think of it less like a wall, and more like a boundary defined entirely by distance and time. Beyond that horizon lie regions of space that we can never observe, never reach, never receive a signal from, no matter how long we wait or how advanced our instruments become. It isn't a matter of technology. It's a matter of geometry. The universe itself is expanding too quickly for information to ever cross that gap. As time goes on, this horizon doesn't stay fixed. It tightens. It draws inward. Regions that were once observable slowly slip beyond reach, one by one, disappearing not in a flash, but the way a tide slowly pulls back from the shore, revealing more and more empty distance where connection used to be possible. And when that happens, something quietly profound occurs. Different parts of the universe stop simply being far apart and become genuinely, permanently separated. Not just distant neighbors anymore, but entirely disconnected realms, unable to ever influence one another again. No light passing between them. No gravity reaching across. No possibility, ever again, of contact. It's worth sitting with that thought for a moment. Two regions of the same universe, born from the same origin, expanding outward from the same beginning, drifting so far apart, so irreversibly, that they become as good as separate universes entirely. Not through destruction, simply through distance. As this separation continues, galaxies themselves drift farther and farther from one another. The vast cosmic web that once connected clusters and filaments of galaxies begins to thin, stretch, and eventually break apart entirely. Space that once felt structured, threaded with galaxies like cities connected by long invisible roads, begins to feel more like scattered lights in an ever-expanding darkness. The cosmos becomes, quite simply, emptier. Not all at once, but steadily, the way a bustling town might slowly empty out over generations, until only a few lit windows remain scattered across an otherwise quiet landscape. Eventually, this isolation becomes so complete that each remaining region of the universe becomes its own separate pocket. Its own island. Colder than before. Emptier than before. Surrounded not by neighboring galaxies or clusters, but by vast, silent gulfs of space that will never again be crossed. Imagine, if you can, standing within one of those future pockets. Looking outward, in every direction, and seeing nothing. Not because there's nothing left in the universe, but because everything else has drifted beyond the edge of what could ever be seen, or touched, or known. It's a haunting kind of loneliness, in a way, cosmic in scale, yet strangely quiet. No violence. No collapse. Just distance, growing patiently, until connection itself becomes impossible. And it's within pockets like these, isolated, cooling, and increasingly empty, that the next great chapter of the universe's story quietly unfolds. The story of the stars themselves and how, one by one, their long lives finally come to an end. For most of cosmic history, stars have been the great engines of light and structure in the universe. Burning brightly, sometimes for millions of years, sometimes for many billions, converting hydrogen into helium, and helium into heavier elements, releasing light and heat as a byproduct of that long, steady process. It's easy to think of stars as permanent fixtures, scattered points of light that have simply always been there, and always will be. But every star, no matter how massive, no matter how brilliant, is running on a finite supply of fuel. And so, inevitably, gradually, stars begin to burn out. Small stars fade slowly, cooling over immense stretches of time, sometimes lasting so long that even now, none of the universe's smallest stars have had enough time to complete their life cycles. Larger stars burn faster, brighter, and more violently, ending their lives in dramatic explosions, or collapsing inward into extraordinarily dense remnants. But whether slow or sudden, quiet or explosive, the outcome is always the same. Eventually, every star exhausts what once made it shine. As this pattern repeats itself, again and again, across countless galaxies, something else begins to happen throughout the universe as a whole. New stars stop forming. Star formation depends on abundant clouds of gas and dust, dense enough, and undisturbed enough, to collapse under their own gravity and ignite new nuclear fusion. But as galaxies drift apart, and existing matter continues to spread out across the widening universe, these clouds become thinner, more diffuse, less capable of collapsing into anything new. Little by little, the raw material needed to build new stars begins to run out. Not disappearing entirely, but spreading so thin, across such vast distances, that it becomes physically incapable of clumping together the way it once did, gathering, condensing, sparking new light. Star formation doesn't end all at once, in some final, dramatic moment. It simply becomes rarer and rarer, until eventually, it stops happening at all. This entire period, this immense stretch of cosmic history filled with active star formation, burning stars, and glowing galaxies, is what astronomers call the stellar era. From a human perspective, this era already feels almost unimaginably long, encompassing everything we've ever observed, everything we currently understand as the universe in action. And yet, even this era, vast as it seems, is only one chapter in a much longer story. Because eventually, the stellar era gives way to something new, something scientists refer to as the degenerate era. The name might sound harsh, almost unsettling, but in this context, degenerate refers to a very specific physical state of matter, not decay in the way we might normally think of the word. This is the era where active star formation has completely ceased. Where no new stars ignite, anywhere, in any galaxy, at any time. Where the last generation of stars has already lived out its life, and burned through whatever fuel remained. What's left behind, scattered throughout the increasingly dark and empty universe, are stellar remnants, the quiet, cooling leftovers of stars that once burned brightly. White dwarfs, the dense cores left behind by smaller stars. Neutron stars, unimaginably compact remnants of larger stellar explosions. Black holes, regions where gravity has become so extreme that not even light can escape. These remnants don't create new light in the way stars once did. There's no more active fusion, no more nuclear reactions lighting them from within. Some of them, like white dwarfs, still radiate a faint, lingering warmth, the last echo of the fire that once burned inside them, slowly fading over almost incomprehensible spans of time. Others, like black holes, emit no light at all, existing simply as dense, silent points of gravity, drifting through an increasingly empty cosmos. Picture, if you can, what a universe like this might look like. No new stars igniting in the darkness. No fresh light being born anywhere. Just the last, fading embers of a once brilliant era, scattered thinly across galaxies that themselves are drifting farther and farther apart, in a universe growing colder, emptier, and quieter with every passing age. It's a strange kind of beauty, really. Not the bright, dazzling beauty of a sky full of living stars, but something softer, quieter. The lingering, gentle glow of an ending that took unimaginable spans of time to arrive, and will take even longer still, to finally, completely fade away. Even the stellar remnants that outlast the stars themselves are not, in the end, truly permanent. Because within the long, quiet stretch of the degenerate era, something even more fundamental begins to unravel, the very atoms that make up ordinary matter. For as long as humans have studied the physical world, atoms have felt like the bedrock of reality. Small, stable, unchanging building blocks, the same yesterday as they'll be tomorrow. But on timescales far beyond anything we can intuitively grasp, some physicists believe that even atoms themselves may not last forever. At the heart of this idea is something called proton decay. Protons, the positively charged particles found in the nucleus of every atom, have always been assumed, at least on the timescales relevant to everyday life, to be essentially stable. But certain theories in physics, especially those attempting to unify the fundamental forces of nature, suggest that protons might not be permanent after all. That given enough time, unimaginably long stretches of time, a proton could spontaneously decay into smaller particles. If this is true, the implications ripple outward into something almost impossible to picture. Because if protons decay, then atoms, which depend on protons to exist, cannot remain intact forever either. Slowly, gradually, ordinary matter as we understand it begins to lose its structure. Not through explosion, or destruction, or any dramatic event. Just through a slow, statistical unraveling, atom by atom, particle by particle, spread across timescales so long they dwarf even the age of the stellar remnants we've already described. Some especially speculative models take this even further, suggesting that eventually, every atom in the universe, every remaining trace of ordinary matter, could dissolve completely. Not immediately. Not within any time frame a human mind could meaningfully hold on to. But eventually, given enough time, which the universe, in this far future, has in abundance. It's worth pausing on how strange this idea really is. We tend to think of solid things, planets, remnants, even the cold, dark husks of long-dead stars, as things that simply exist, indefinitely, once they're formed. But if proton decay is real, then even these things are temporary. Not permanent monuments left behind by the stellar era, but slowly fading remnants of a temporary structure, dissolving quietly back into something even more basic, even more diffuse. Whether or not proton decay actually occurs remains one of the open questions in physics, something scientists continue to search for evidence of, patiently, carefully, without yet finding a definitive answer. But if it does happen, it means that the era of stellar remnants, however long it lasts, however ancient it becomes, is itself only a phase. A temporary structure resting atop a universe that is still, quietly, continuously moving toward greater simplicity. And it's within this same immense stretch of time, as ordinary matter slowly fades from relevance, that a very different kind of object rises to take its place as the last true structure left in the universe. This is often called the black hole era. By this point in cosmic history, nearly everything else has already faded. The stars have long since burned out. New star formation ceased ages ago. Even the stellar remnants, the white dwarfs and neutron stars that once lingered as quiet embers, have largely dissolved away, if proton decay holds true, or simply gone dark and cold in the more conservative picture. What remains, dominating this unimaginably distant future, are black holes. Black holes, in this era, become the last major organized structures anywhere in the universe. Not because they are common, or numerous, but because they are among the few things still complex, still structured, still distinct enough from the surrounding emptiness to be called a thing at all in any meaningful sense. It's a strange kind of legacy for black holes to hold. For most of the universe's earlier history, they were seen as points of destruction, regions where matter and light disappear, swallowed beyond any hope of return. But in this far future era, they become something else entirely, quiet monuments. The last remaining architecture in an otherwise increasingly formless universe. But even black holes, despite their reputation for permanence, for being the ultimate point of no return, are not actually eternal. Over spans of time so long they make even the degenerate era feel brief by comparison, black holes begin to fade. Not through collision, or collapse, or violence of any kind, but through an extraordinarily slow, quiet process of radiation. This process is known as Hawking radiation, named after the physicist who first predicted it. The idea itself is delicate and strange, rooted in the odd behavior of empty space at the quantum level, where particles and their antiparticle counterparts can briefly appear near the edge of a black hole's boundary. In certain rare circumstances, one particle falls inward, while the other escapes outward, carrying away, ever so slightly, a small amount of the black hole's mass and energy. It's an almost imperceptibly slow process. For the smallest black holes, it might complete over relatively short, though still incomprehensibly long, timescales. But for the largest black holes, the supermassive giants that once sat at the centers of galaxies, this process could take a truly staggering amount of time to complete. And yet, given enough time, it does complete. Black holes are not permanent. They lose mass, slowly, continuously, through this radiation, shrinking bit by bit, until eventually, they evaporate entirely. Some estimates place the evaporation of the very last, largest black holes at somewhere around 10 to the power of 100 years into the future. A number so large that writing it out in full would fill more space than most human minds could meaningfully process. It isn't just a long time. It's a length of time that makes every other timescale we've discussed so far, the age of stars, the length of the stellar era, even the slow dissolution of atoms, feel almost immediate by comparison. When the last black hole finally radiates away its final trace of mass, fading silently into nothing, it marks the true end of anything resembling structure in the universe. No more stars. No more stellar remnants. No more atoms, if proton decay holds true. And now, no more black holes either. What remains, after this final structure disappears, is something almost impossible to picture in any traditional sense. This is what some call the dark era. After the stars have gone. After the black holes have evaporated. After even the last organized structures the universe ever produced have faded completely away, all that remains is radiation and scattered particles, drifting silently through an unimaginably vast, cold, and empty expanse of space. No light sources left to shine. No gravity wells left to gather matter together. No structure left to organize anything, anywhere, into anything resembling the stars, galaxies, or even simple remnants that once filled the cosmos. Just a thin, diffuse whisper of particles and radiation, spread almost perfectly evenly, drifting quietly through the dark. It's a strange kind of stillness to imagine. Not empty in the way a room is empty, but empty in a way that stretches across distances too vast to meaningfully picture, and across time so long that long itself starts to lose its ordinary meaning. And yet, even here, in this profoundly quiet, dark, and nearly featureless universe, something remains. A faint trace of everything that came before, still drifting, still present, still real, even if nothing more will ever happen to it again. By the time the universe reaches this final stage, almost nothing remains that could be called structure, in any sense we'd recognize. No galaxies holding together under gravity. No clusters, no filaments, no great cosmic web threading through space. What was once an intricate architecture, built over billions upon billions of years, has thinned into something almost featureless, a vast, quiet expanse with nothing left to define one region from another. This is the stage many refer to, simply, as the Dark Era. It's a fitting name, in its own quiet way. Not dramatic. Not violent. Just dark. Empty. Still. The Dark Era doesn't begin with any single dramatic event. There's no moment where a switch is flipped, no instant where the universe suddenly goes still. Instead, it begins gradually, in the long silence that follows after the very last astrophysical objects finally fade away. The last white dwarf, cooling into an unlit ember. The last neutron star, radiating its final trace of heat into the surrounding dark. The last black hole, if enough time has passed, evaporating into nothingness through the slow work of Hawking radiation. Once these final objects are gone, what's left behind is almost impossible to describe using the language we normally reserve for things. Thin radiation, drifting outward in every direction. Scattered remnant particles, spread so far apart from one another that meaningful interaction becomes essentially impossible. No clumping. No gathering. No structure of any kind, holding itself together against the overwhelming vastness of empty space. The universe, in this state, becomes nearly inert. It's a word worth sitting with for a moment, inert. Not destroyed. Not erased. Simply, unreactive. Unchanging. A universe that still technically exists, still contains its scattered particles and faint traces of radiation, but no longer does anything, in any meaningful sense of the word. Almost no physical processes remain possible at this point. No chemistry, because chemistry requires atoms interacting, exchanging energy, forming and breaking bonds, none of which remains feasible in a universe this spread out, this cold, this profoundly still. No nuclear processes, because there's no fuel left to burn, no density left to sustain fusion, no structure left capable of producing the pressures and temperatures those reactions require. Even the more basic thermodynamic processes we've spoken of already, processes driven by simple temperature differences, become impossible here, because temperature differences themselves no longer exist. Everywhere you might look, in this far future universe, the temperature would read the same. Not similar. Not nearly identical. The same. Precisely, exactly, everywhere. And this uniformity leads to something particularly strange to consider. In a universe with no temperature differences left anywhere, and no physical processes still occurring, time itself begins to lose its practical meaning. This is a delicate idea, worth approaching gently. Time, as we experience it, is deeply tied to change. We measure it through motion, through decay, through processes unfolding, one step following another. A clock ticks because gears move. A candle marks time because wax slowly melts. Even our own bodies measure time through countless tiny biological processes, constantly shifting, constantly changing, moment to moment. But in a universe where nothing changes anymore, where every process that could happen has already happened, where perfect equilibrium has been reached, and nothing remains to disturb it, time, in any meaningful, measurable sense, essentially stops mattering. Not because time itself ceases to exist, in whatever technical sense physicists might define it, but because there's nothing left for it to measure. No events. No processes. No change from one moment to the next. Imagine, if you can, an endless, undisturbed stretch of stillness so complete that whether a single second passes, or a trillion years, absolutely nothing is different. That is the strange, quiet nature of time within the deepest reaches of the dark era. And yet, even within this profound stillness, there is one last, faint whisper of activity left to consider, something some physicists describe using a particularly evocative phrase. The idea of a last photon. It's a beautifully strange image, when you think about it. Long after the stars have gone dark. Long after the black holes have quietly evaporated. Long after almost every other process in the universe has fallen silent, there remains, drifting through the vast emptiness, a scattering of photons, tiny packets of light, remnants of ancient processes that occurred unimaginably long ago. These photons don't behave the way starlight does, blazing brightly across space. Instead, they are impossibly faint, stretched by the endless expansion of space itself, redshifted so dramatically over such immense timescales that their wavelengths grow longer and longer, their energy fainter and fainter, until they carry almost no discernible energy at all. Some discussions describe this as a kind of last photon scenario, a moment, so distant and abstract that it can barely be called a moment at all, where the very last meaningful packet of light finishes its journey, and fades beyond any possibility of detection or interaction. Not because it's destroyed, but because it becomes so stretched, so faint, so deeply diluted by the sheer scale of space, that it no longer meaningfully exists as anything you could call light, in any practical sense. After this point, if such a point can even be meaningfully defined, the universe approaches something remarkably close to perfect uniformity. No detectable photons carrying information. No discernible particles interacting in any meaningful way. Just an unimaginably faint, uniform hum of energy, spread as evenly as anything could possibly be spread, across the entirety of an endlessly expanding cosmos. At this stage, what little energy still exists doesn't come from stars, or particles, or radiation left over from ancient events. Instead, the evolution of the universe becomes dominated by something far stranger and more abstract, the energy inherent to empty space itself. This is sometimes described in connection with what scientists call dark energy, or more generally, the intrinsic energy of the vacuum. Even in a region of space containing nothing, no particles, no radiation, no matter of any kind, empty space itself appears to carry a very small, persistent amount of energy. And in this far future era, once everything else has faded away, this quiet, ever-present vacuum energy becomes the dominant force shaping whatever remains of cosmic evolution. It's a profound thought, in its own quiet way, that after everything, after every star has burned out, every black hole has evaporated, every photon has faded beyond detection, what remains isn't nothing, exactly. It's something even more fundamental. The bare, quiet energy of space itself, continuing on, indifferent, patient, permanent, in a universe that has otherwise gone almost entirely silent. In this final, near-timeless expanse, one more quiet truth settles over everything: communication itself, in any form, between any two remaining regions of the universe, becomes utterly impossible. It's worth thinking, for a moment, about what communication actually requires. A signal, of some kind, traveling from one place to another. Light, carrying information across space. Gravity, subtly influencing one mass because of another, somewhere nearby, or even impossibly far away. Even the simplest form of influence, one particle affecting another, depends on some kind of connection, some pathway allowing cause to lead to effect. But by this stage, in the vast, cold stillness we've been describing, no such pathway remains. Space has expanded so completely, so relentlessly, that the distances separating any two remaining points have grown far beyond anything a signal, even one traveling at the speed of light, could ever hope to cross. What little energy remains is so thinly, so evenly spread, that even if something wanted to reach across that distance, wanted to send some trace of itself outward into the surrounding dark, there would be nothing left with enough coherence, enough structure, enough energy, to make that journey meaningfully. Every remaining point in the universe becomes, in the truest sense, entirely alone. Not lonely in the way we understand loneliness, as beings capable of longing for connection, but alone in a more fundamental, physical sense. Cut off. Isolated. Beyond any possibility of ever again exchanging so much as a single photon with anything else. Some discussions give this final condition a particularly evocative name: total dilution. It's a phrase that captures, almost poetically, exactly what has happened. Not destruction. Not disappearance. Simply, dilution. Everything that once existed, all the matter, all the energy, all the light and structure and complexity built up over billions of years, has been spread so thin, across such an unimaginable volume of space, that it no longer resembles anything we would recognize as substantial. A universe so diluted that presence and absence become almost indistinguishable from one another. There's another term, even more speculative, sometimes used to describe this strange, far future condition: cosmic virtuality. It's a delicate, almost philosophical phrase, gesturing towards something difficult to fully define. The idea that in this final state, what remains of the universe exists in some vague, barely defined sense, present, in principle, according to the equations and models physicists use to describe it, and yet so faint, so without structure or interaction, that its existence becomes almost theoretical. A universe that technically continues, without truly doing anything that could be called existing, in any meaningful, tangible way. It's strange, isn't it, how a story that began with blazing stars and roaring nuclear fire, with galaxies swirling brightly across the young cosmos, ends here, in something so quiet, so faint, that scientists reach for words like dilution and virtuality, simply trying to describe a state that ordinary language was never quite built to capture. And yet, as strange and distant as this vision feels, it isn't a modern invention. The roots of this idea, this quiet, patient unraveling of the universe, stretch back much further than you might expect, not to modern telescopes, or satellite data, or supercomputer simulations, but to a much older, more grounded place. To the steam engines, and laboratories, and careful thermodynamic experiments of the 19th century. It was during this period, in the mid-1800s, that scientists first began to seriously understand the laws governing heat, energy, and work. This was the era of the Industrial Revolution, when engineers were obsessively studying how engines converted heat into motion, how energy transformed from one form into another, and crucially, how much of that energy was inevitably lost along the way, dispersed as unusable waste heat. Out of this practical, industrial curiosity came something profound: the foundations of thermodynamics as a formal science. And it was within this new framework that one particular physicist began to wonder whether these same principles, discovered through steam engines and laboratory experiments, might apply not just to machines, but to the universe itself. That physicist was Lord Kelvin. Kelvin, already well known for his work in temperature and thermodynamics, took a bold conceptual leap. Instead of confining these ideas to engines and closed laboratory systems, he extended them outward, to their largest possible scale, to the cosmos as a whole. If energy naturally disperses, if usable heat naturally flows toward useless, evenly spread warmth, then perhaps the same fate awaited the entire universe, not just a single machine, or a single room. This was, in many ways, one of the first moments where the everyday physics of heat and energy collided directly with questions about the ultimate fate of everything. Kelvin framed what he was proposing quite directly. Heat death, in his view, was not some abstract speculation, but a direct, unavoidable consequence of the laws of thermodynamics already being studied and confirmed in laboratories around the world. If the second law held true, that entropy naturally increases over time, then applied across the entire universe, indefinitely, it seemed to lead inevitably toward the same quiet, cold stillness we've been describing throughout tonight's journey. But Kelvin's thinking didn't stop simply at proposing this eventual outcome. He went further, raising a much deeper, much more unsettling question, one that would come to be known as the heat-death paradox. Here's the heart of Kelvin's puzzle. If the universe naturally moves toward increasing entropy, toward eventual equilibrium, toward heat death, and if the universe has existed forever, infinitely far back into the past, with no beginning at all, then shouldn't that process have already finished by now? Think about what infinite time truly means. Not a very long time. Not billions, or trillions, or any number of years, no matter how large. Truly, endlessly, infinitely long. If entropy has been increasing throughout all of that infinite past, moving steadily and irreversibly toward maximum disorder, toward perfect equilibrium, then no matter how slow that process might be, given infinite time, it would already be complete. The universe, in other words, should already be dead. Cold. Uniform. Silent. Not still filled with burning stars, and active galaxies, and complex structures like the ones we observe tonight, all around us, in a universe clearly still very much alive with activity and change. This was Kelvin's paradox, a genuine, deeply puzzling contradiction between what thermodynamics seemed to predict, and what astronomers could plainly observe simply by looking up at a night sky, still filled with countless shining stars. And this paradox, strange as it might sound, became one of the pivotal arguments used against the idea that the universe could be infinitely old. If an infinitely old universe should already have reached equilibrium, should already be locked into that same cold, dark, uniform stillness we've spent this entire journey describing, and yet, clearly, it hasn't, then perhaps the universe isn't infinitely old at all. Perhaps it has a beginning. A starting point, sometime in the finite past, however distant, from which all of this activity, all of these stars, all of this structure and change, first began. This single observation, simple as it sounds, carried enormous weight in the history of cosmology. It became one of the key pieces of reasoning employed by scientists questioning whether the universe could stretch backward through infinite time, without any starting point at all. And this question, this genuine puzzle first raised by Kelvin in the 19th century, remains, in many ways, still relevant today. A key issue, still discussed among physicists and cosmologists, still worth reflecting on quietly, late at night, when the mind drifts easily toward questions this vast, the observation that an infinitely old universe, viewed strictly through the lens of thermodynamics, should, by now, already have settled into the very equilibrium we've spent this entire episode describing is still lying somewhere in our own future. It's a strange thought to end on, in its own way. That the very quiet, distant fate we've been imagining throughout tonight, the fading stars, the evaporating black holes, the vast, cold, uniform stillness stretching outward across unimaginable spans of time, was first glimpsed, in careful, thoughtful form, not through powerful telescopes gazing outward into deep space, but through a physicist's quiet reflection on steam and heat and the simple, patient laws governing energy itself. A reminder, perhaps, that even the grandest, most cosmic questions, the ultimate fate of everything that exists, often begin in the smallest, most ordinary of places. A cooling cup of tea. A dying flame. A single, careful mind, wondering quietly, late into the night, just how far these simple, familiar patterns might truly extend. This simple observation, that stars still burn brightly across the night sky, tonight, and every night, turns out to be one of the most powerful pieces of evidence available to answer Kelvin's paradox. Because if the universe truly were infinitely old, if entropy had genuinely been increasing across endless, unbounded time, then the stars filling our sky right now shouldn't exist at all. There would be no light left to see. No structure left to form. No active, burning process anywhere, in any galaxy, because everything that could happen already would have happened, endlessly long ago, settling long since into that same quiet, cold equilibrium we've spent so much time describing tonight. And yet, here we are, surrounded by starlight, living within a universe still very much in motion, still filled with young stars igniting, still filled with galaxies actively forming, still filled with more activity, more change, more difference than a universe in true equilibrium could ever contain. The continued existence of stars, quite simply, proves that equilibrium has not yet been reached. It's a beautifully direct piece of reasoning, when you think about it. Not requiring complex equations, or advanced instruments, or elaborate theoretical models, just a simple, quiet look upward, into a clear night sky, and the recognition that if the universe had truly existed forever, none of what we're seeing should still be here to see. This is, in many ways, one of the gentle reassurances tucked within an otherwise cosmic, distant story. The heat death we've explored across this journey isn't something happening now, or soon, or any time within a timescale meaningful to any living thing. It's a future so distant, so unfathomably far removed from tonight, that the simple fact of stars still shining above us stands as quiet proof of just how early, in cosmic terms, this present moment truly is. But even so, once we allow our minds to travel forward, past the stars, past the black holes, past even the faintest last photon drifting through an unimaginably diluted universe, there remain a few strange, speculative possibilities, ideas some physicists and thinkers have allowed themselves to imagine, when wondering what, if anything, might exist within, or even after, such profound and lasting stillness. One of these ideas comes from a physicist named Freeman Dyson, who once imagined something remarkable, the possibility of an eternal civilization. Dyson's thinking followed a careful, almost hopeful logic. If a civilization, however advanced, wished to survive indefinitely into this cooling, darkening future, it would need to adapt, continuously, to an ever colder, ever more diffuse universe. Perhaps, Dyson suggested, such a civilization could slow its own processes, its thinking, its actions, its very experience of time itself, in careful proportion to the universe's declining energy. Thinking more slowly, but never stopping entirely. Stretching every act of thought, every moment of experience, across longer and longer intervals, always finding just enough usable energy remaining to continue existing, even as the available energy grew fainter and fainter with each passing age. It's a strange, beautiful, almost melancholic idea, intelligence, not defying the ultimate fate of the universe, but adapting to it. Slowing patiently alongside the universe's own gradual decline, always present, in some faint, careful way, stretching existence outward across nearly endless time, without ever quite reaching a true, final end. Whether such a thing could actually happen remains deeply uncertain, resting on assumptions about physics and energy that stretch far beyond what we can currently test or confirm. But as a thought experiment, it offers a strangely comforting possibility, that awareness, in some form, however slow, however faint, might persist even into the universe's coldest, quietest chapters. A very different, much stranger idea, tied to these same distant timescales, is something known as the Boltzmann brain paradox. This idea begins from a curious, unsettling question. In a universe defined by random fluctuations, however faint, however rare, could it be possible, given truly enormous stretches of time, for a fully formed, self-aware mind to spontaneously arise, not through evolution, not through birth, not through any of the processes we associate with the emergence of consciousness, but simply through chance? Through an extraordinarily improbable, but not technically impossible, random fluctuation of particles, briefly assembling themselves into something capable of thought, before dissolving once again into the surrounding emptiness. It's a deeply strange thought experiment, one that unsettles rather than comforts. And it raises even stranger questions about probability itself, suggesting that in a universe existing across truly infinite time, such a randomly assembled, momentary consciousness might actually be far more statistically likely to occur than the kind of consciousness we experience now, built gradually, over billions of years, through stars, and planets, and the long, patient unfolding of evolution. Most physicists treat this less as a serious prediction, and more as a philosophical puzzle, a kind of cautionary tale about the strange conclusions that can emerge when reasoning carelessly about infinite time and probability. But it remains, nonetheless, one of the more haunting ideas occasionally discussed when imagining what, if anything, might still occur within the deep, quiet stretches of the universe's distant future. These strange possibilities are rooted in a broader, equally strange idea, the notion that quantum fluctuations, tiny, random shifts occurring naturally at the smallest scales of reality, might continue to produce unusual, unexpected phenomena, even deep within these late, otherwise quiet cosmic eras. Quantum mechanics tells us that even in what we might consider a true vacuum, empty space is never perfectly, absolutely still. Tiny fluctuations, tiny fleeting appearances of energy, particles, and antiparticles, continue to flicker in and out of existence, even in regions containing nothing else at all. Most of these fluctuations are utterly fleeting, disappearing again almost immediately after they arise. But over truly vast stretches of time, spans so long they make even the evaporation of black holes seem brief by comparison, it becomes statistically possible, however unlikely, for larger, more unusual fluctuations to occur. This leads to one particularly fascinating idea explored by some cosmologists, the concept of Poincaré recurrence. This idea borrows from an older area of mathematics and physics called statistical mechanics, originally used to describe how systems made of many particles evolve and behave over time. One curious implication of this framework is that, given a truly, genuinely infinite stretch of time, any physical system, no matter how disordered it becomes, may eventually, purely by chance, return to a state resembling its earlier, more ordered condition. Applied to the universe as a whole, this leads to an almost dizzying possibility that a low-entropy universe, a state resembling order, structure, and complexity, similar in some vague sense to the early universe we know today, could theoretically reappear, spontaneously, out of the vast, quiet uniformity of heat death itself. Not through any grand cosmic event, but through pure, statistical chance, playing out across timescales so vast that vast barely begins to describe them. Some have taken this reasoning even further, wondering whether sufficiently rare, sufficiently powerful thermal fluctuations, arising randomly within this deep cosmic stillness, might somehow trigger something resembling a new Big Bang-like event, a fresh beginning, emerging unexpectedly from the ashes of an ending that once seemed truly final. Others approach this same possibility through a slightly different lens, considering the strange behavior of quantum tunneling, a phenomenon where particles, under very specific and unusual conditions, can spontaneously transition between states in ways that seem to defy ordinary expectations. Some speculative models suggest that this same underlying mechanism might, under sufficiently rare and extreme circumstances, potentially seed the birth of an entirely new universe, springing forth from what once appeared to be nothing more than empty, uniform stillness. It's important to hold these ideas gently, with a sense of curiosity rather than certainty. None of them represents settled science. Each rests on extending known physical principles into territories so far beyond anything we can observe or test, that they remain, fundamentally, speculative, more philosophical wondering than confirmed prediction. And yet, there's something quietly beautiful in allowing the mind to wander this far. To imagine that even within the deepest, coldest, most profound stillness the universe could ever reach, nature might still hold some faint, almost imperceptible potential for renewal. Not guaranteed. Not expected, in any conventional sense. But present, perhaps, as the faintest possibility, waiting quietly within the endless statistics of an infinite and patient cosmos. Let's try, for a moment, to actually give shape to the number involved in these speculative recurrence timescales, though shape may be the wrong word entirely, because numbers this large stop behaving like ordinary numbers at all. Some proposed estimates for Poincaré recurrence place the timescale at somewhere around 10, raised to the power of 10, raised to the power of 56 years. Not 10 to the 56th. 10, raised to an exponent that is itself 10 to the 56th. It's worth sitting quietly with that distinction for a moment, because it changes everything about how large this number actually is. To put this in some kind of perspective, without pretending it's truly graspable, the total number of atoms in the observable universe is estimated to be somewhere around 10 to the 80th. A staggeringly large number on its own. And yet, the recurrence timescale we're describing doesn't just exceed that number. It exceeds it so completely, so overwhelmingly, that the number of atoms in the universe becomes almost meaningless by comparison, a single grain of sand, next to a desert stretching beyond any horizon the mind could ever construct. These timescales, quite simply, sit beyond comprehension. Not difficult to comprehend, the way a large crowd, or a long journey, or even the age of the universe itself might be difficult to comprehend, with effort and patience and the right kind of visualization. Genuinely, fundamentally beyond it. There is no useful metaphor, no gentle comparison, no way to make a number like this feel real, or intuitive, or meaningfully long in the way we experience long stretches of time now. It exists, mathematically, as a valid possibility within certain models, and yet it stretches so far beyond anything resembling human experience, or even cosmic experience as we've discussed it throughout this journey, that it becomes something closer to a philosophical curiosity than a genuine prediction. It's worth remembering, gently, that ideas like this, Poincaré recurrence, Boltzmann brains, spontaneous low-entropy fluctuations, exist at the very edges of speculative physics. They're fascinating to consider, precisely because they stretch our imagination to its absolute limits. But they remain far from settled, far from certain, and far from universally accepted, even among physicists who study these questions closely. Because, in fact, heat-death itself, as certain and inevitable as it can sometimes seem when described in careful, patient detail, is not universally agreed upon as the final, certain fate of the universe. There remain genuine, active challenges to this picture, alternative possibilities that some physicists find equally, or even more compelling. One of the more intriguing challenges suggests that the universe might never actually reach true equilibrium at all, that instead, it could remain permanently, persistently out of balance, no matter how much time passes. This idea traces back to a physicist named David Laser, who proposed something now often referred to as the entropy gap. Laser's reasoning approached the problem from an interesting angle. We often think of entropy simply increasing, steadily, towards some fixed, maximum ceiling, a point where disorder finally reaches its highest possible level, and stays there, permanently. But Laser suggested something more subtle. What if the maximum possible entropy a system could have isn't fixed at all? What if, as the universe continues expanding, that theoretical ceiling for maximum entropy actually grows too, and grows faster than the universe's actual entropy can keep up with? If that's true, then rather than actual entropy slowly catching up to some fixed finish line, and settling permanently into equilibrium once it arrives, the finish line itself keeps moving, continuously expanding outward, faster than entropy can close the gap. This creates something genuinely fascinating to consider, a persistent, ongoing gap between how disordered the universe actually is, and how disordered it theoretically could become. And as long as that gap remains open, as long as maximum possible entropy continues outpacing actual entropy, true equilibrium, true heat death, might never actually be reached at all. Not because entropy stops increasing, but because the target it's chasing keeps moving further away, faster than it can ever catch up. It's a subtle, elegant idea, one that complicates the otherwise straightforward picture we've spent so much of tonight exploring. Rather than a universe smoothly settling into stillness, this suggests something more dynamic, a universe perpetually chasing balance, without ever quite achieving it. Always tending toward equilibrium, in principle, yet never fully arriving, because the very definition of equilibrium continues shifting, continues expanding, right alongside the universe itself. This same tension, between entropy building up and the search for alternative cosmic outcomes, becomes especially important when considering another possible model for the universe's fate, the idea of cyclic universes. Some cosmologists have proposed models where the universe doesn't simply end, in any single, final sense, but instead repeats, expanding, cooling, perhaps eventually contracting, only to bounce back into a new expansion phase, beginning again, cycle after cycle, stretching backward and forward through an essentially endless series of cosmic ages. It's an appealing idea, in some ways. A universe that renews itself, rather than fading permanently into stillness. But these cyclic models face a persistent, difficult challenge, the same entropy we've discussed throughout this journey. Because if entropy genuinely increases over time, as the second law of thermodynamics suggests, then even in a cyclic universe, entropy wouldn't simply reset itself, cleanly, at the start of each new cycle. It would carry over, accumulating gradually, cycle after cycle, making each new cycle slightly more disordered than the one before it. Given enough repetitions, given enough cycles stretching across sufficiently long timescales, this accumulated entropy creates a serious problem for the idea of endless, self-sustaining cosmic cycles. Rather than repeating indefinitely, in perfect, unchanging repetition, a cyclic universe governed by increasing entropy would gradually change from cycle to cycle, generally trending toward greater and greater disorder, even across what was supposed to be a repeating, renewing process. This is, in many ways, one of the reasons many physicists find heat death a more probable long-term outcome than models involving endless cosmic cycles. Entropy's steady, patient accumulation doesn't disappear, simply because a universe hypothetically resets itself. It carries forward, quietly, cycle after cycle, ultimately favoring a single, gradual drift toward final equilibrium, rather than a clean, endlessly repeating pattern free from thermodynamic consequence. And yet, even within this broader picture, favoring heat death over cyclic alternatives, the specific details, the precise mechanisms, and even the exact timelines involved, remain very much active areas of ongoing research and revision. In fact, some of the more recent discussions among physicists suggest that our understanding of heat death's timeline may be shifting, even now, as new theoretical work continues to develop. One particularly interesting area of new research proposes something quite unexpected: the idea that the curvature of spacetime itself, not just the presence of black holes, might be capable of causing a slow, gradual evaporation of particles. This is a subtle, technical idea, but its implications are fascinating. Previously, Hawking radiation, that slow leaking away of mass and energy we discussed earlier, was understood specifically in relation to black holes, and the extreme curvature of spacetime found at their boundaries. But newer theoretical work suggests that even regions of space without black holes, simply by virtue of the universe's overall expansion and curvature, might produce a similar, extremely gradual process of particle creation and decay. If true, This would mean that particle evaporation, in some very slow, very subtle form, might not be limited only to the extreme conditions found near black holes. It could, potentially, occur more broadly, as a natural consequence of the universe's own expanding geometry. Related proposals build on this same idea even further, suggesting the possibility of Hawking-like decay processes occurring even in the complete absence of black holes altogether, driven purely by the underlying structure and curvature of an ever-expanding universe. These are still very early, very speculative ideas, actively being explored, debated, and refined within the physics community. They don't overturn the broader picture we've spent this entire journey describing, a universe gradually cooling, gradually spreading, gradually approaching a state of profound stillness. But they do remind us that even something as seemingly settled as the end of the universe remains, in many important respects, an active, evolving area of scientific understanding. Perhaps that's a fitting thought to rest on, for now. That even here, considering timescales so vast they exceed all comprehension, and outcomes so distant they may never truly be observed, human curiosity continues, patiently, quietly, refining and revising its understanding, one careful idea at a time. Much like the universe itself, slowly, gradually, moving forward, toward whatever quiet answers may eventually be found. These new theoretical proposals about space-time curvature and particle decay don't simply add an interesting footnote to the story. They actually reshape, in some fairly significant ways, how long the entire process we've been describing tonight might actually take. According to some of this newer research, matter itself may decay faster than physicists had previously assumed. Not just protons, slowly dissolving according to older, more conservative models, but a broader range of matter, breaking down through these newly proposed curvature-based processes, at a pace quicker than earlier calculations suggested. This has some particularly interesting implications for objects we've already spent time discussing tonight, the quiet, cooling stellar remnants that linger long after the stars themselves have gone dark. Dead stars, white dwarfs, and neutron stars alike, along with the mysterious, still not fully understood substance known as dark matter, may vanish from the universe earlier than previously predicted, according to these revised models. It's a strange thing to consider, that even the patient, lingering embers of long-dead stars, objects we imagined earlier as remaining stable for almost inconceivable stretches of time, might dissolve away sooner than older calculations once suggested. And if these remnants disappear earlier, the broader transition toward the universe's final, quiet state also shifts earlier, following closely behind. Rather than stretching across the almost incomprehensibly long timescales discussed in some of the earlier, more conservative estimates, this newer research suggests the overall progression toward heat death's final chapter could unfold considerably sooner. Some of this newer work goes even further, arguing that certain final stages, previously thought to require inconceivably longer timescales, might actually arrive noticeably sooner than earlier models proposed. According to some of these recent studies, the universe's ultimate transition toward this final, quiet state may occur sooner than researchers had previously calculated, based on these newly considered decay processes. One particularly notable revised estimate places this transition at somewhere around 10 to the 78th years, a number still almost impossibly vast by any ordinary standard, but meaningfully smaller, by an enormous margin, compared to some of the far larger estimates, stretching toward 10 to the 100th years or beyond, that we discussed earlier regarding black hole evaporation. It's worth pausing gently here, to appreciate just how strange and fluid our understanding of these timescales really is. Even numbers as vast, as seemingly abstract, as 10 to the 78th, or 10 to the 100th, remain open to revision, refinement, and ongoing scientific debate. The broad picture, a universe slowly cooling, spreading, and quieting over time, remains fairly consistent across these different models. But the precise pacing, the exact timeline this transformation follows, continues to shift, subtly, as research progresses, and new theoretical tools become available. And yet, even with these revised timelines in mind, it's worth stepping back, for a moment, to remember something important. Heat death itself, no matter which specific timeline eventually proves most accurate, remains only one proposed ending among several genuine possibilities still considered by cosmologists today. It isn't a guaranteed, universally agreed upon certainty. It's the leading candidate, based on what we currently observe, particularly the universe's accelerating expansion. But it isn't the only story physicists have seriously considered, when imagining how the universe's long journey might eventually conclude. One of the more prominent alternatives, quite different in character from the slow, quiet fading we've spent this entire journey exploring, is something known as the Big Crunch. Where heat death imagines an ending defined by expansion, dilution, and cold, the Big Crunch imagines almost the exact opposite. In this alternative scenario, rather than continuing to expand indefinitely, the universe's expansion would eventually slow, stop, and then reverse entirely. Gravity, rather than losing its influence across an ever-widening cosmos, would instead reassert itself, pulling everything, every galaxy, every star, every remaining trace of matter, back together, inward, rather than outward. In this picture, the universe doesn't drift apart into isolated, cooling pockets, scattered further and further from one another across ever-growing gulfs of empty space. Instead, it does the opposite. Space itself begins to contract. Galaxies that once drifted apart begin, slowly at first, and then with increasing speed, to move back toward one another. Distances that once stretched outward begin instead to shrink, steadily, inevitably, drawing everything closer, and closer, and closer together. Where heat death is a story of dispersal, the Big Crunch is a story of gathering. Where heat death ends in cold, the Big Crunch would end, instead, in heat. As the universe contracts, densities increase. Matter, once thinly spread across vast cosmic distances, becomes compressed into smaller and smaller volumes. Temperatures rise, rather than fall, as everything is pushed closer together, with less space remaining between one object and another. Rather than a slow fade into darkness and cold, this scenario imagines a very different kind of ending, one defined by rising heat, increasing density, and eventually, an almost unimaginable final collapse. In some ways, it echoes the universe's own distant beginning, played out in reverse. Instead of an initial, unimaginably hot and dense point expanding outward into everything we now observe, a big crunch would imagine everything we currently observe collapsing back down, inward, toward that same kind of extreme density and heat, reversing billions of years of cosmic expansion in one final, dramatic contraction. It's a vivid, almost dramatic alternative, quite different in tone from the quiet, patient stillness of heat death. Rather than fading gently into cold and silence, this ending would conclude in searing heat, an overwhelming density, a fiery, violent finale, rather than a slow, peaceful fade. Of course, current observations, particularly the accelerating expansion we've discussed at length throughout this journey, make heat death considerably more likely, based on everything we currently understand. But the Big Crunch remains a genuine, seriously considered possibility within cosmology, a reminder that even our most careful, well-supported scientific models remain, in some sense, still open. Still being tested. Still being refined, patiently, against whatever new observations the universe continues, quietly, to reveal to us. Beyond heat death, and beyond the fiery alternative of the Big Crunch, there remains at least one more possibility, one that, in many ways, feels even stranger and more unsettling than either of the endings we've already discussed. This possibility is known as the Big Rip, where heat death imagines a slow, gentle dilution, stretching across almost incomprehensible spans of time, and the Big Crunch imagines a dramatic, fiery collapse. The Big Rip imagines something else entirely, an ending defined not by slow dispersal or sudden collapse, but by an ever-accelerating, runaway expansion, growing so powerful, so relentless, that it eventually overwhelms every structure in the universe, no matter how small or how tightly bound. In this scenario, the same accelerating expansion we've discussed throughout tonight's journey wouldn't simply continue at a steady, gradual pace. It would keep intensifying, faster and faster, until eventually, this expansion becomes strong enough to overcome even the strongest forces holding matter together. Galaxies would be torn apart first, followed by individual star systems, then planets, then eventually, in this scenario's most extreme final moments, even atoms themselves would be ripped apart, unable to hold together against the sheer, overwhelming force of space expanding around them. It's a vivid, almost violent image, quite different from the peaceful stillness we've spent most of this journey exploring. Rather than a slow fade into cold and quiet, the Big Rip imagines a universe pulled apart, quite literally, thread by thread, until nothing remains intact at any scale, however small. Alongside this idea, physicists also consider another unsettling possibility, known as vacuum instability. This concept rests on a particularly delicate feature of quantum physics, the idea that what we currently understand as empty space, the quiet vacuum stretching throughout the cosmos, might not actually represent the most stable configuration possible. Some theoretical models suggest that our universe's vacuum could exist in what's sometimes called a false vacuum state, stable enough to persist for extraordinarily long stretches of time, and yet not truly, fundamentally the lowest possible energy state available. If this is true, then somewhere, at some unpredictable moment, a small region of space could theoretically transition into a lower, more stable vacuum state. And if that happened, this new, more stable state wouldn't stay contained. It would expand outward, at the speed of light, fundamentally altering the laws of physics within the region it passes through, essentially rewriting the fundamental rules governing that portion of the universe, permanently and irreversibly. It's an unsettling thought precisely because of its unpredictability. Unlike heat death, or even the Big Crunch, both of which unfold gradually, and somewhat predictably, according to well-understood physical principles, vacuum instability could, in theory, occur suddenly, and without any prior warning whatsoever. What determines which of these very different possible endings actually awaits the universe, ultimately, comes down to one central, still not fully understood factor: dark energy. Dark energy, that mysterious force believed to be driving the universe's accelerating expansion, sits at the very heart of each of these different possible outcomes. Depending on precisely how dark energy behaves, not just now, but across the unimaginably long stretches of time we've been discussing throughout this journey, the universe's ultimate fate could shift dramatically from one possibility to another. If dark energy remains essentially constant, behaving the way our current best models suggest, then heat death, the slow, patient dilution we've spent most of tonight exploring, remains the most likely outcome. But if dark energy changes, even subtly, over these vast timescales, everything could shift. If dark energy were to weaken, gradually losing its outward push over time, the universe's accelerating expansion could slow, and potentially even reverse. In that case, heat death might never actually occur at all. Instead, gravity could eventually reassert itself, pulling everything back together, leading not toward the cold, quiet ending we've described, but toward that dramatic, fiery alternative, the Big Crunch. On the other hand, if dark energy were to strengthen, rather than weaken, becoming more powerful over time rather than remaining steady, this could push the universe toward that far more violent possibility we just described, the Big Rip, where expansion accelerates so dramatically that it eventually tears apart every structure in existence, right down to the atomic level. Because of this deep uncertainty, some cosmologists now treat what's called the cosmological constant, the mathematical term traditionally used to represent dark energy's steady, unchanging influence, not as a fixed, permanent value, but as something potentially evolving, shifting subtly over cosmic time, rather than remaining perfectly constant forever. This possibility, that dark energy itself might change, has taken on renewed importance recently, as newer surveys and observational studies, specifically designed to measure dark energy's behavior with greater precision, have begun producing results. Rather than settling old questions, these new dark energy surveys have, in some ways, revived them. Some recent measurements hint, tentatively, at the possibility that dark energy's strength might not be perfectly constant after all, potentially varying subtly over cosmic history in ways not yet fully understood or confirmed. These new dark energy measurements haven't provided a clear, definitive answer. If anything, they've introduced additional uncertainty into a question many scientists once considered close to settled. Rather than confirming, with increasing confidence, that heat death represents the universe's inevitable fate, these newer observations remind us just how much remains genuinely unknown about one of the most fundamental forces shaping our cosmic future. Some physicists hope that future particle physics experiments, probing the fundamental nature of matter, energy, and the vacuum itself at ever deeper levels, might eventually reveal hidden instabilities, or unexpected behaviors, capable of finally resolving some of these lingering uncertainties. Perhaps confirming, more definitively, whether dark energy truly remains constant, or whether it shifts, subtly, across cosmic time, ultimately determining which of these very different possible endings the universe is actually moving toward. For now, though, no such definitive answer exists. And perhaps that's the most honest, most important thought to carry forward, as we bring tonight's long, quiet journey to a gentle close. The universe's ultimate future, whether it ends in the slow, patient stillness of heat death, the fiery collapse of a big crunch, the violent unraveling of a big rip, or perhaps something else entirely, not yet imagined or discovered, remains, quite genuinely, an active area of scientific research. Not a settled conclusion, written finally into textbooks, closed off from further questioning. But an open, ongoing exploration, still unfolding, still being refined, still inviting careful thought and patient study from each new generation of scientists who look upward into the night sky and wonder. Much like the universe itself, vast, patient, and still quietly unfolding, our understanding, too, continues to grow. Slowly, carefully, one quiet, careful thought at a time.